Okay, so section 1.13 or 113 on page 110, again, flip through the book. This one's mainly all vocabulary, and there was a full video on this section. I didn't teach this section, so you're going to want to watch that video. But make sure you know what a constant is, what a term is, what factors are, coefficient, expression versus equation. And then if you keep flipping through, make sure you know what a polynomial is, and a monomial, binomial, trinomial. And I think that's about it on this one. So if we look at this, remember the word terms. This kind of looks like a plus sign right there. So terms are things that are added. Factors, kind of have the O in there, so think of multiplication. So terms are things that are added, factors are things that are multiplied, but it kind of depends on what you're paying attention to. So for example, if I'm looking at the x plus 3 with the x plus 9, when parentheses touch, there's multiplication in there. So as a chunk, these chunks are factors. But if I look within and I'm looking at just the x and the 3, like what's happening with the x and the 3? Well, they're being added. So the x and the 3 compared to each other are terms. The x and the 9 are being added, so compared to each other, they're terms. But if I combine them as a chunk and say x plus 3 compared to x plus 9, then suddenly as chunks, they're factors because they're being multiplied. If I look at this example here, these things are being added, and maybe I'll put some other stuff in here. I'm going to have to pause this. My eyes are watering because of allergies. So here I'm going to pause and come back. All right, I'm back here. So on this thing right here, we have all these things. Every chunk that's being added is a term. So again, remember terms adding. So like this is a term, and the sign goes with it. So like positive 8x, positive 9y, negative 9x squared, and positive 9. So that negative, that minus goes into there as a negative. So these are all terms that are being added. Now, within them is some, like when this touches, that means multiplication. So 2 and x squared compared to each other are factors. 8 and x compared to each other are factors because they're being multiplied. Same with 9y, negative 9 and x squared are factors compared to each other, okay? The other thing is the number that's in front of a variable is called the coefficient. So this is a coefficient, coefficient, coefficient. Negative 9 counts as a coefficient, and even 9 you could call a coefficient technically to x to the 0 power. And then the other word is a constant. A constant is just a number. Usually in algebra we would call this a constant and we call these coefficients, but technically these are constant as well. This is always a 2, always 8, always 9, always negative 9 and 9. So technically even coefficients are constants. But I would say the best name for this is a coefficient, and the best name for this is probably a constant. So variables. So again, this section, just make sure you read the vocab. The other thing is polynomials are when we have some algebra junk. You have to have nice exponents in polynomials, so you can't have like the square root of x plus 8. That is not a whole number exponent. Actually, that is actually to the half power. So if you ever thought, can you have fractions for exponents? The answer is yes, like a half is a square root. So you can't have decimals like 1.5 minus 8x plus 3, not a polynomial. So you can only have nice exponents on your x's. Your numbers can be whatever you want. So if you want like 3/4 x squared minus the square root of 7x plus 9, totally fine. Exponent's nice, and then we have a constant there. So as long as your powers of x are to the whole numbers, and again, negative numbers are not allowed either. It has to be whole numbers, positive whole numbers. And those are polynomials. And then the other thing is monomials, binomials, and trinomials. So if you have one chunk of algebra stuff with nice exponents, it's a monomial. If you have two chunks of algebra stuff, two chunks with nice exponents here, these are binomials. And then if you have 3 pieces of nice, again, algebra stuff with nice exponents, oopsie, 3, then that's a trinomial, okay? And we can have polynomials with like 4 things, but we just don't give them a special name. So these are all nice whole number exponents. And again, I could put a, number in there. I could put a fraction in front. It's just the coefficient, or sorry, it's just the exponent on the x here. If those are nice, then this is still a polynomial. It just has 4 terms in it, so we don't give it a special name. All right, go ahead and look at section 1.14, and I will pick up there next. Okay, the next section, as far as vocab goes, there was inductive and deductive. And remember, these are kind of backwards. So when they say, hey, Sherlock Holmes has really great deductive reasoning, that's actually wrong. When a bunch of information comes in, so information, they all start with I, info comes in, and you generalize it to a rule, that's inductive reasoning. So you look at a bunch of evidence and then you're like, aha, I think so-and-so did it. Kind of like the game of Clue, right? You get all these clues and then finally you have your hypothesis as to who did it with what weapon in what room. That's inductive reasoning, okay? Deductive is when you apply a rule that already exists to other situations. So someone gives you a rule like, oh, I don't know, area of a circle is pi r squared. You see a circle and it has a radius of 6 inches. You put that in the formula, you do the formula, get an answer. That's deductive, okay? So when you apply a law that someone else created, that's deductive. Inductive is when you figure out the pattern, you figure out the rule yourself, okay? Those are 2 of the vocab. The other one was counterexample. And remember, a counterexample is when you do the math and you prove that it's false. So someone might say, anytime you square a number, it always gets bigger. And so then you're like, is that true, right? Now, to prove it true is hard, like you have to do a mathematical proof. But to prove it false, you just need to find one example where it's not true. So you might be like, okay, 8 squared is 64. It got bigger. It went from 8 to 64. And then you might try 10 and you're like, well, it got bigger again. 10 squared is 100. So then think about negative numbers, 0, 1, fractions. 1 and 0 are always kind of weird. So 0 squared is 0. Notice it didn't get bigger. It stayed the same. Same thing with 1. 1 times 1 is 1. It didn't get bigger. It stayed the same. But notice with fractions, like a half squared would be a half times a half, which is a fourth. That actually got smaller when you squared it. So if someone says that when you square a number, the answers always say bigger than your original number, that's not true, because here it's a half and I squared it and it got smaller. It became a fourth. So a counterexample is when you prove something false just with one example. You don't need a lot, just one. All right, the other thing in this section is the patterns. Now, it's possible that you could have a pattern where, like, I don't know, you add 1, then you add 2, then you add 3, then you add 4. And so you have this pattern, you're like, okay, I added 1, then I added 2, then I added 3, then I added 4. And it's true that, there's a pattern. You'd add 5, then add 6, and so forth. But that's not a pattern we are going to write a formula for on the test. So it's not geometric or arithmetic, okay? So we're going to look at, say I give you a pattern that goes 4, then 7, then 10, then 13. This kind would be on the test. All right, and so you look, it's not getting big fast, so it's probably getting big by adding. So I'm like, oh, that's 3, that's 3. Oh, the patterns add 3. So you just fill in the blanks, you keep adding 3. And again, you might want to double check on a calculator, and you guys can double check my math, make sure it works. So add 3, so 3 is 16. I think I'm okay. Okay, sorry, I had to edit a little bit there, so if it glitched, I apologize. Okay, so since this is an adding pattern, it is arithmetic. And arithmetic starts with an A, and so does adding, so they go together. It's an adding pattern. And if it's arithmetic or an adding pattern, it's also what we would say is linear. And remember, on linear, the variable is low. So linear, the variable is low. So how do these work? Well, you always have a start, and then you have plus or minus whatever your number is that you're adding or subtracting. And then remember, if you start at the first term, if you don't start at 0, then this is always going to be n minus 1. Always, 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 because it's always going to be off by 1. Because remember, real life starts at 0, but unfortunately, sequences start at 1. All right, so my start is at 4. plus, what am I adding all the time? I'm adding 3, right? So plus 3, and then n minus 1, because I started at the first term. Now, remember, in real life, you can cheat if you want and go back. So if real life starts at 0, so start at 0th term. Then you have your add or subtract your number, and then it's always just going to be n. You don't need the n minus 1 because it's going to work out. So if instead of adding 3, if I go backwards in time, I'd subtract 3. 4 minus 3 is 1. And notice if I want to get to the, let's see, 6th term, how many times would I add 3? Well, I would add it once, twice, 3 times, 4 times, 5 times, 6 times. So do you see how the 6 matches adding 3 6 times? So I just use n. I'm not off. So my 0th term, if I went back in time, is 1. So I'm starting at 1, and I am adding 3 all the time, and then I just need n. And what this does is it predicts the future. So say I want to know what the 6th term is. So I'm going to sub 6 in here and just see if my formula will predict it. 1 plus 18 is 19, and that looks exactly like what I want. Okay. All right. The other type I'll put on the test, I'm not going to put the ugly ones on, so you don't have to worry about that, is say that I have something like, let's see, I had another one here. Okay, so like 5, 15, 45. All right. And so this time it appears that I'm multiplying by 3. So times 3, and I need to find my calculator. It kind of fell on the floor here, so I got to grab my other one. So I'm just going to keep multiplying by 3 to fill in the blanks, okay? So if I clear it, hopefully. So 45 times 3, I'm just typing that in my calculator, and again, let me put my lamp on. Sometimes that helps. Maybe. That's 4 times 3. All right, let's try 45 times 3. And I get 135. And then take 135 times 3, looks like 405. And again, you can see that exponential gets big fast. So if it's getting big fast, it's probably a multiplying pattern, not adding. So times 3, times 3, times 3, times 3. Okay. Now again, how do these sequences always start at the first term? So if that's going to be your formula, then these are multiplying, so it is geometric. So geometric is a multiplication. You can see kind of maybe that O in there. So geometric is a multiplication pattern. And this is the same as exponential. So in these case, your exponent or your variable is going to be in the exponent. So your variable is not low. Your variable is going to be high in the exponent. Okay, it's going to be up there, all right, because of repeat multiplication. And so if I look at this, what's my formula going to look like? Well, if you start at the first term, so if you start at the first term, then you're going to multiply by whatever your number is. So you're going to multiply whatever your number is. And then your exponent is going to be n minus 1 if you're starting at the first term. So in this case, my first term is 5. And I am multiplying by 3 all the time. Okay, and you can use parentheses if you want. And then I'm off by 1 because I started at the first term, so it's going to be n minus 1. And again, if you want to cheat, these type of patterns, real life starts at the 0th term, right? Like a baby being born or blast off, right? It's at time 0. 1 means you're 1 year old. Or when you first start a job, it's 0. But a year 1 would be like a year later, a month later, okay? So if you start at the 0th term, then you're going to have your times your number, and then you're not going to need n minus 1 because the number of times of multiplying 3 is going to match what term you're on. So if I go forward by multiplying by 3, to go backwards, I'm going to divide by 3. So 5 divided by 3 is 5/3. I'm not going to write it as a decimal because I'd be rounding. So I'm just going to take 5 divided by 3 and write it as 5/3. 5 divided by 3 is 5/3. So that's my starting term times, what am I multiplying by? 3 to the n. Or you could have like 5/3, you know, times 3 to the n, or parentheses to the n. Okay. Now again, say I want to predict the, let's see, first, second, third, fourth term. All right. So if I take 5/3, my formula, times 3, and n would be to the 4th. So that means I'm going to multiply by 3 4 times. Is that true? 1 time, 2 times, 3 times, 4 times. And so you can see why if you start 0, the number of multiplying matches your term. And so if I type this in my calculator, so to check it, it should work out, and my calculator is going to not work here, but you guys can type this in. It will equal 135.